Okay, so today's lecture, we're going to introduce Bayesian methods. So what you saw in the assignment, or what you'll be seeing in the assignment and in the lab class, is attempts to deal with overfitting by approaches like validation, cross-validation. That's what we looked at last week. But the question 3 is another approach which aims to, well, in some sense, you can think of it as not fitting models because it's a different approach to data modeling. And the ideas behind it, it's sometimes known as Bayesian modeling. I don't much like the name Bayesian modeling because it sounds like it's a cult or something. And it's not a cult, it's just a sort of sensible approach to dealing with uncertainty. It's a particular approach to dealing with uncertainty. So another thing it's sometimes called is inverse probability. And with luck, you might understand why it's called that by the end of the lecture. So before I talk about Bayesian modeling, I just wanted to go back to something that we had in the first lecture and we've talked about since. That was this issue of two simultaneous equations with two unknowns is easy to solve. So if the two unknowns, if you've got data which is x1 and x2, there's inputs, and you've got targets as t1 and t2, you have two equations here. You know t1, t2, x1, x2, you don't know m and c. So you can solve for those unknowns, and we talked about that in the first lecture. And what it turns out is that the solution is that m is the gradient, and c is the offset going through the y-axis. Great. So the problem was that if we added an additional point, that gives us a third equation and two unknowns. And this is what we call an overdetermined system. There's more equations than there are unknowns. And how did we choose to deal with that? What we added was what we called a noise model. Now, what I think of this noise model as doing is generating something that we don't observe, which we sometimes call a latent variable, which is what the corruption was in each experiment. So we've sort of augmented our model with this epsilon, which is saying how we corrupt away from what we believe is going on. This is what we think is going on, but then there's some stuff we're not modeling coming from the world. And that's coming from a Gaussian distribution. So that's how we motivated least squares. We did maximum likelihood in this model. That's in effect what we've done so far. And the noise model is what we're using for is we're accepting that we're not, with our linear model, we're not modeling the entire system. And the noise model is giving us this mismatch between what we observe and the data. The Gaussian model for noise can be justified by an appeal to the central limit theorem, but it's sometimes wrong. And we sort of mentioned that student T models, we talked about that lighthouse thing. We're not going to look at those models in detail, but just to know that the Gaussian model isn't the only model that can be used here for epsilon. It's just a simple model that we're happening to use. The philosophy of the noise model, these could even not be identically distributed or whatever. So that's how we got least squares. But now I want to take you somewhere else, which is actually the opposite end of that coin, an underdetermined system. So an underdetermined system, how do you deal with a situation where you've only got one observation? So now, before we had two observations for two unknowns, and we could solve that, we've described how we deal with an overdetermined system. We add a sort of slack variable, which is the noise, which accounts for the model mismatch. But how can we deal with this? We want to fit a linear regression in this situation. Any ideas? We've got one observation, and we want to fit a straight line to the observation. Anyone think of anything we could do? Any ideas? Silly ideas, whatever.
Horizontal line?
Horizontal line, that's a good idea, actually. That's a good idea. What is the horizontal line going to suggest about if you make a horizontal line, what's your assumption for m?
0.
M is 0, yeah. So the horizontal line is making an assumption that m is 0. And once you've made an assumption about m, you can fit a line. Okay? So I'm actually going to do that. It's an excellent suggestion, but I'm actually going to make an assumption for c. I'm going to assume, because we can compute m given c, I'm going to assume that c is 1.75. Okay? Does that seem reasonable? C is 1.75, and now I can find out what m is. It's good, isn't it? So now we fitted a line. Does anyone see any problems with that?
We can fit infinite lines.
We can fit infinite lines. So where do we get c from? Well, here's another c. This c is minus 0.77. Here's another c. This one's minus 4. Here's another c, minus 0.718. Another c, and so on. Now there's no noise here, so all these lines are going through. But what could I do? Instead of saying I'm just going to choose c, how can I represent a family of c's? A belief about multiple c's? Anyone got any ideas? We know it, we've seen it.
Some kind of distribution.
Some kind of distribution over c. Very good. That's Bayesian inference. We make an assumption about a distribution for the parameters. So in this case, the assumption I made was that c is drawn from a Gaussian with 0 mean and a variance of 4, so a standard deviation of 2. That's got its own parameters as well, right? But it's less constraining than saying, oh, I think c's 1.2 or I think m is 0. It's allowing you to consider a family of solutions. Do we get the sense of that? So we can't fit, as someone pointed out, there's infinite possible solutions we could fit going through this line, because we could choose c anywhere along the real line, and then we get all solutions out.
So you're choosing a value of c based on some form of belief.
Based on some form of belief, yeah. So we have a belief in c. That's a very good point. We're choosing a value in c based on some form of belief, what we would call an a priori belief, a belief before we see the data. So that's exactly the right point. We're choosing c. So we did see the data in this case. But let's pretend we haven't seen the data and you know you're going to have to do this. You might have a belief about what values of c you believe are reasonable. So before I come into this room and I'm told, well, you're going to have to measure students' heights, I might have an a priori belief about what the average height will be. Yeah? So I might believe in my head that the average height is going to be 1.7 meters plus or minus 20 centimeters. And I can encapsulate that in a distribution or a density. And that's the Bayesian method. That you represent your a priori beliefs in a distribution. Given then an observation, you get posteriori beliefs. So in this case, these posteriori beliefs are some distribution of lines. Because the standard deviation is here, the belief about the intersect is down here, most of those lines tend to move in this direction, yeah? Because we're saying that c, we believe it's drawn from a normal density with standard deviation of 2. Okay, any questions about that? Because it's actually quite an important philosophical jump. And it's the main thing you need to know for doing Bayesian inference, that when you're doing Bayesian inference, instead of dealing with individual parameters and saying, I'm going to learn exactly what c is, and that there's some definite c, you start out with a belief over c, once you've got your belief over C, you observe data, and then you update your belief over C. Yeah? And you use probability to do it. One issue here, and this is an issue for Bayesian inference, what if we wanted to be uniformly uncertain about C? What would happen? So we've specified it's around, but what if we wanted to say C could be anything? Can we do that? One way of thinking about that question is, what would it mean if we wanted to represent that C could be anything for a normal density? What could we do to this normal density to make it cover all possible values for C? Anyone? So it's covering between 2 and minus 2 now. If we wanted it to cover between the entire real axis, what would we have to do to the variance? Yeah. That would not be a normalizable distribution. So the density you would get would not normalize. So you can take the limit as this density goes to infinity, and then you get, remember in the Gaussian density, the variance appears at the front underneath. It doesn't normalize anymore. So you can't do that. You have to say something. But you could say plus or minus 10,000. You could say plus or minus 10 million. But it's a problem. And you can do it if the region of interest is bounded. So if you know a parameter is between 0 and 1, you can have a flat prior that says, I don't know what the answer is. But for when you're operating across the real line, because the set is sort of uncountably infinite, you can't do that. Okay. So before, what we did is we took the regression problem, and this is the one you've been working in the lab, and we said we've got a likelihood for the data that says the probability of the data set given these parameters W and the variance sigma squared is given by a product of Gaussians, where the mean of each Gaussian is given by W transpose phi I, where phi I is some basis, could be a polynomial, could be a radial basis function, like you're working on in the lab. And sigma squared is the noise variance. Oh, just one point I guess I haven't covered that I wanted to cover. I think this is my sort of summary lesson from this. And something I haven't seen other people describe it in this way, but this is the way I like to think of it. The interesting thing was that we're solving this problem of underdetermined systems by introducing probability. How did we solve the overdetermined system? Introducing probability. Now, importantly, we put the probability in two different places. The lack of data here leads to uncertainty about our model of the world, the bit that we believe in, the linear relationship. We have uncertainty in those parameters. In the overdetermined system, the uncertainty is going in to the bit of the world that we're not modeling. And that distinction maps onto two words which we'll cover later. That this is what we'd call epistemic uncertainty. Epistemic means that it's uncertainty that we could in principle resolve. We'll come back to that. And the other uncertainty is called allegoric uncertainty, where the unmodeled uncertainty that we can't actually resolve. Okay. So what's the Bayesian perspective? The Bayesian perspective is to take, the maximum likelihood perspective was to take this function, we look at the negative logarithm of it, we called it an error and we minimized it, and found a point estimate for W. The Bayesian perspective is different. We integrate across W. Now this is very interesting because to optimize, what do you need of this log likelihood? What do we compute for the log likelihood? When I ask you to do this into the exam, what's the first thing you'll think when I say find, differentiate? Yeah. The opposite of integration. So you differentiate because you're trying to find a minima. In the Bayesian approach, you integrate. But you can't integrate across W alone because there's no guarantee that this will normalize. The likelihood itself won't normalize. You need to include that prior distribution. So you use, as we'll see, the product rule to give you a joint distribution of t and w, and then you integrate out w. And you're left with a probability of t given all possible values of w. And that turns out to be a crucial thing in model selection. It's called the marginalized likelihood. You can also find another density, which is the probability of w given t. So that's the posterior probability, what your distribution of parameters is given your observations. So you start with a prior probability over c, but in the general case, a probability over w. That represents your early beliefs about what w should be. Then you observe data, and the data is in the form p of t given w. Once you've observed the data, you update your belief about what the model is to get the posterior. These are samples sort of from the posterior. Does that make sense? So it's a different process, very different process to what we've been doing. But the marginal likelihood can be used for model selection. And in fact, that's what you get asked to do in part 3 of the lab class, to compute the marginal likelihood for the different models you fit, the different basis functions. This is known as the Bayesian approach. So we use Bayes' rule to invert probabilities in the Bayesian approach, right? That's a rule we covered at the beginning. I think I've got it in these slides somewhere. I hope I have. If not, I'll write it on the board. It's not called, this is important, 98% of people who naively use machine learning don't understand this. It's not called the Bayesian approach because of Bayes' rule. Bayes' rule is not a controversial thing at all. It's just a rule. It's derivable in like 2 steps. It's called the Bayesian approach because the term Bayesian refers to the treatment of the parameters as stochastic variables. And this is something that in his paper, Thomas Bayes did. And for early statisticians, this is very controversial. Oddly, for very early physicists like Gauss and Laplace, it wasn't controversial at all. They did it all the time. So there's some controversy that arose through statistics, but never appeared in physics. And for me, it's not controversial, but I'm just letting you know that some people think it's controversial. Fisher apparently developed the term Bayesian to make it sound like a belief system. It sounds like a religion, doesn't it? But before that, it was called inverse probability. And that's all it is, inverse probability. I prefer that term, but perhaps in general, people are more familiar with the term Bayesian. Okay, so just to review why Fisher pointed at Bayes when inventing this thing, it's actually the way that Bayes introduced the Bernoulli distribution. So the Bernoulli distribution is just the simple probability of, say, a coin flip. So I flip a coin and it comes up head or tails. Heads with probability 0.5, tails with probability 0.5. But it could be a biased coin. Heads with probability 0.3, tails with 0.7. Yeah? So the Bernoulli distribution, I don't think we've looked at it. I did last year, I had it in the early lectures. But it's very simple. You're going to come up with this in future lectures. But just to briefly look at it, pi is the probability of heads. T is 1 if the coin is heads, and 0 otherwise. And this mechanism here is just a switch. So pi to the 1 is what? Pi, yeah. Pi to the 0 is what? 1. So if t is 1, then this pi to the 1 is pi. This term, which is 1 minus t, will be what if t is 1? No? 1. Yeah? So it's pi to the t times 1 minus pi to the t to the 1 minus t. So if t is 1, this term is just 1 and the answer is pi. If t is 0, this front term is 1 and the answer is 1 minus pi. It's just a mathematical switch. It looks a little bit ugly, but it's like a mathematical statement. If t equals 1, the probability is equal to pi. If t equals 0, the probability is equal to 1 minus pi. It's useful because you can now optimize this sort of thing and do all sorts of stuff like that. But it's just a mathematical switch. So all this distribution says is probability of t, capital T being 1 is equal to pi. The probability of capital T being 0 is equal to 1 minus pi. Yeah? Makes sense? So that's the Bernoulli distribution, very simple, used in classification. And Jacob Bernoulli introduced it in terms of an urn. So I've got cyan balls and white balls in here. And what he said is that if you've got a bag of cyan and white balls and you reach in and randomly grab one ball, the probability of it being white will be the proportion of whites over the total number of balls, yeah? And the probability of it being cyan will be the number of cyan over the total number of balls. So the proportion of probability being white, pi, is equal to white, the number of whites divided by the number of cyans plus whites, and 1 minus pi is obviously the complement, and equal to the proportion of cyan balls. That's how Jacob Bernoulli described the Bernoulli distribution. I don't think that Bayes was necessarily aware of this description, but he described the same distribution in quite a different way. What's noticeable about this is inside, philosophically, and this is just a philosophical thing, inside that bag there is a number of balls that's fixed, right? It's not a stochastic variable. Certainly not a stochastic variable in the noise sense that we've been dealing with before. Bayes set it up in a different way. He talked about a ball being sent across a table. So this is, imagine a billiard table. He doesn't say billiard table, but imagine a billiard table and you get a ball and you roll it left and right and it bounces and it lands uniformly across the sides of this table. The position where it lands, we draw a line. Yeah? And then we get another ball and do the same. This one happens to land on the left. Another ball, that lands on the left as well. Another ball, that lands on the left. Finally, one lands on the right. The probability of it landing on the left, if we assume that it's going to land in a random space, which might not be true, but let's make that assumption, is given by the position where the first ball landed, yeah? Which itself was a stochastic variable. So this is why they call it Bayesian, because he set up the Bernoulli distribution where the parameter is a stochastic variable, whereas in Bernoulli's case, he didn't. Now, that's about interpretation of parameters. It's not about use of Bayes' rule. And that's what Bayesian means. People talk about naive Bayes networks. You might learn about them with Trevor. They're not Bayesian. They're just using Bayes' rule. And Bayesian inference has become so popular, people want to use it as a brand name now. Oh, I'm doing something in a Bayesian way. They're very often not. They're just using Bayes' rule. Philosophically, Bayesianism is about placing, or inverse probability is about treating parameters as a stochastic variable. I believe in it 100%. I mean, I don't see why you wouldn't treat it as a stochastic variable. It's a way of encoding a belief, as was pointed out before, about a parameter. You do it with a distribution. We reject utterly fuzzy logic in this school of thought. Utterly and totally. We see there's nothing that fuzzy logic can do that you can't do with probability, and it's entirely a construct which is unnecessary. So when people are doing Bayesian inference, they're using that to encode uncertainty. Fuzzy logic is an entirely separate construct someone's built to encode uncertainty, and people claim it does different things. People who do Bayesian inference typically reject it utterly, because they say probability is the right way of encoding uncertainty. You don't need to come up with fuzzy sets, all these strains, fuzzy membership functions. You've already got it with probability and Bayes' rule. That's all you need. Makes a very simple world. Okay, so that's the sort of overview of Bayesian probability with a little bit of history. So the controversy, which I don't really think is a controversy because I don't see anything controversial about it, that exists, relates to treating this epistemic uncertainty as aleatoric uncertainty. So the way I described it, I mean, I think that these terms are, I really, in some sense, don't think aleatoric uncertainty exists for practical purposes, which is why I don't see that there's a controversy. But what do people mean by these terms? So why would and I'll explain why I don't think it exists, but ignore that bit because I'm trying to teach the orthodoxy. So the paper lands on the floor, right? Where it lands versus where I'm dropping it from, the uncertainty of where it lands, I would say is aleatoric uncertainty. Or most people would say it's aleatoric uncertainty. Yeah, it's stochastic. It's similar to that sort of noise in the linear model. My model might be that I expect the paper to land where I dropped it because I've done Newtonian physics and I don't understand air. Yeah. So my model is a Newtonian physics without air model in it. So I expect the paper to drop. And all the stuff it does in between, actually it did land quite close that time, is aleatoric uncertainty because I'm not modeling that because I'm a physicist. Well, a high school physicist. Yeah. That's all aleatoric uncertainty. And I really like this example. Before a football match, the uncertainty about the result is aleatoric uncertainty. All sorts of stochastic things can happen. Yeah? Anything can go on. But if I watch a recorded match, and sometimes I do this, like I can't watch a match live, so I make sure I don't know the result, and then I go and watch a recording of the match, pretending it's live, it's just as exciting, isn't it? The uncertainty is the same, but the uncertainty is epistemic, because I can always go and check on the internet who won. So, and I even did that once. I tried watching the Rugby World Cup semi-final, England versus France, was it last year or something? And the match had finished, and I was trying to watch it. I hadn't had a chance to watch it, so I didn't know the result, and I was watching it. But England played so appallingly that I got annoyed, and I went and looked at the result on the computer and saw that France had won, and it saved me a load of angst. You can't do that in the case that the match is ongoing, yeah? But the uncertainty up until I looked at the computer is the same as far as I'm concerned. So epistemic is uncertainty that we could, in principle, know. So another sort of example of epistemic uncertainty is, what color socks am I wearing? Anyone have a guess what color socks I'm wearing? Black. Black's good guess. It's a good guess. Any other guesses? Blue? White? Magenta, yeah. I think it's always like, because I know I'm going to ask that question, then it's sort of adversarial, so I might have put some strange color on. And I did think about it, but I'm actually wearing blue socks. If you see a stylish Italian, they'll often match their socks to their shirt. So you know if someone's Italian, you can get information about that, and you can believe their socks are going to match their shirt. But that's epistemic uncertainty. You might be interested in what color socks someone's wearing, and you can have a belief. You can say white's a good guess, gray, black, blue, all good guesses. The outside guess of magenta is an excellent one because you think, well, he knows he's going to ask that question. But if we just see someone in the street, we might think the probability a priori of magenta is small. So that's a way of dealing with beliefs. And the uncertainty there is epistemic. We can, in principle, know it. It's not the same as dropping this piece of paper. Now, I say all that, and there is this distinction. But actually, in some sense, the reason this one's aleatoric is because there's so many things involved that are epistemic. You know, there's actually a bunch of molecules colliding with it. It's just a chaotic system. In principle, you could know, but you can never know because it's so precise.
So in epistemic probability, we basically have a belief, whereas aleatoric uncertainty, we don't.
Yeah, okay, so that's a good point. Yeah, epistemic, well, I think epistemic probability, the question was, do you have a belief epistemic probability and aleatoric you don't? I like the first bit of that statement. That's the controversy, is that people say with epistemic, it's not a probabilistic thing what color socks I'm wearing. That's what they say. But it's true, and then we're representing it with a probability which represents our belief. That's the Bayesian thing. Aleatoric, everyone accepts that's a probability. And the probability is the frequentist definition, which is in the limit as me dropping this infinite times, and we count up where it lands, what's the distribution where it lands? That's a specific case of the Bayesian understanding of probability, which is degrees of belief. And not covering this, but people sometimes talk about betting in order to. At what point would you bet? It's your degree of belief in something, not a repeated number of events. The repeated number of events definition becomes problematic when you start trying to forecast weather for tomorrow, which is probably aleatoric uncertainty, but you can't repeat tomorrow. So we use degrees of belief for that. But yeah, I mean, was that what you were driving at, or were you saying? Yeah. Okay. Okay, so I just to emphasize on that, I think very much in the example I've given you, I almost prefer another definition, which isn't the official one. The official one is the one I've given you. Think football. Epistemic is, you know, I asked this question in the exam, what's the difference between epistemic and aleatoric uncertainty? And I'd given this example, and like still 70% people, well, 70% of people got it, but 30% of them had flipped them around. And I was like, did I teach it the wrong way around or something? Okay, so it's in like last year's exam paper, this is a question. One way I like to think about it, oh, that pen is a flip chart marker. Oh dear, that shouldn't be there. Just wipe that off. Y equals mx plus c plus epsilon. The epsilon is the aleatoric part. I can't spell aleatoric, look at that. Aleatoric. I won't knock marks off if you misspell aleatoric in an exam. The uncertainty over M and C is the epistemic part. Because in principle, if you had infinite data, you could know M and C. Yeah, actually, if you had infinite data. In principle. And I actually tend to think of it from a modeling point of view. It's which part I tend to think that we're putting epistemic part on the model uncertainty, our representation of the world, and the aleatoric part uncertainty is on the bit of the world that we're ignoring. That's the way I tend to think of it, but the official definition is that. So simple Bayesian inference, we've got that likelihood, we've talked about the prior, the belief about parameters before we've seen anything. And these parameters could be something that has a direct meaning, like the color of my socks. You could have a discrete distribution over that. Although that's actually continuous, isn't it, color? Anyway, let's ignore that. The color of my socks, or the parameters of the linear regression. The likelihood gives the relation between the parameters and the data. The likelihood is really important. One way of thinking of it is like the model of the relationship between the parameters and the data. So it contains all your beliefs about how the data would emerge given a set of parameters. We've already seen it, we've already played with it. What sort of things does it encode? I tend to think of the model being specified altogether, and sometimes it's quite hard to separate prior from likelihood. For this stage it's easy, but as you get into non-parametric models, which we're not going to do, it gets hard. One example I like for Bayesian inference is, imagine you have a robot and it's located in a room, yeah? And it has sensors. And these sensors are sonar sensors. And let's say we know the robot's pointing in one direction. So all we want to know is its sort of north-south location and its east-west location in this room. And the robot has a sensor at its front, and it measures with some Gaussian uncertainty the distance to the wall, because it's got a sonar sensor, yeah? And maybe it's got a second sensor pointing out the side. And it measures to the wall some uncertainty distance. Here, the prior would be directly over the robot's location. So the probability of its location, if that's x1 and that's x2, a p of x. The observation of the distance, the perceived distance to the wall, would be encoded in a probability of y given x. So what does that encode here? That says, for any position x in this room, I believe the robot would sense, so if it's just got two sensors, one up, one across, it would sense approximately with a Gaussian distribution this distance and this distance, yeah? So that's the likelihood. Sometimes you can think of it as a sensor thing. In our case, we're just thinking of it as the linear regression term we've already seen. So in this example, once you've seen the wall, you update your belief about where you are. So you have an initial belief which might be sort of uniform. It could be uniform in a box. You observe the wall, you observe your sensors, and then you think, oh, it must be around here, because the sensors aren't that good. But you've seen two sensors, that actually gets you down to around here. Yeah? So that's the posterior. Then the marginal likelihood represents the assessment of the quality of the model. And this allows us to do model selection. So you can even sometimes compare it to other models if you do things right. And ratios of marginal likelihoods are sometimes known as Bayes factors. And people use these to try and estimate which of two models is better. You can never tell absolute correctness with Bayes, by the way. You can never tell you've got absolutely the right model, because you could always envisage coming up with a different model. There's infinite different models you could use, and you can only compare two models relatively. So you can never say, oh, this is the optimal model, because the space of all possible models for any data is enormous. But you can take two models, and you can say, given my current observations, which of these two models is more likely? And select between them. And you do that, well, in statistics they call those Bayes factors. So this is Bayes' rule at the top. I thought I had a slide with it written in mathematical form, but I'll just do that since I seem to have left that off. In terms of the notation we've been using for the regression example, posterior is the probability of W, the parameters of the model, given X, the inputs to the model, and T, the target observations. The likelihood is the probability of the targets given the parameters and X. I'm leaving off sigma squared in the parameters. I should really put sigma squared in the parameters. Now I've run out of space, so let me just shift that. So P of W given X comma T is equal to the likelihood, P of T given W comma X, times the prior. What's the prior over here? P of W, yep. Prior belief in the regression weights. We haven't said what we're going to use for that yet. And the marginal likelihood, well, what's that going to be? So can we have a think? Can anyone tell me what this is? This is the product rule of probability. You should have been rereading this. You need to know this inside out, this stuff. What's that going to be? The multiplication of those two. Product rule of probability. Anyone? That's depressing. P of A given B times P of B is equal to what? P of A comma B. Okay, that's less depressing. Good. P of T given W comma X times P of W. P of T comma W. Very good. So you can ignore the X in this case. It just stays conditioning on the right because it doesn't have a prior there. So P of T given W comma X, P of W is equal to P of T comma W given X. What do we need to multiply the left-hand side by to also get that joint distribution? If I wanted an equality here, this is incorrectly written. If I want this to be an equality, what do I need to multiply on this side? 1 over P, not 1 over PW, because this is P of W given X comma T. Let me make it easier. What do I need to multiply this side by? P of T. Very good. P of T. That's called the marginal likelihood. So that equality is true, and the derivation for Bayes' rule just involves putting P of T down here. Now what we actually also have, given X, is the probability of T given X. Now what does this represent? This process, how do we get this, first of all? How do we get P of T given X? What rule do we need of probability for that? Some rule which involves in continuous space integration. So P of T comma W given X integrated over W is equal to P of t given x. That's why the whole thing involves integration. Because in order to, this is one thing you're interested in, the posterior distribution. You want to know this. What do I believe about the parameters after I've seen the data? You're also interested in this guy anyway, just for model selection. Because look at what this guy says. And you can just, once you start reading probability densities, I mean, it's so bad that our education, I think, should be probability all the way, because it makes your life so much easier if you can handle these things and look at them. This distribution almost is saying in words the probability of t given x, and implicitly the model choice, right? We haven't really included that. But implicitly my choice of model classes. But let's just ignore the choice of model class. It no longer depends on w. Yeah? It actually depends on the prior you chose for w. We've hidden that away, we've not notated that. But it doesn't depend on w itself. So we can ask the question, what's the likelihood for this model? You can look at it as a different type of likelihood, yeah? We call it the marginal likelihood. It's got parameters. If we want to enunciate them, there's the sigma squared, which is the variance parameter, and we're going to use alpha as our variance over w in a second. So the marginal likelihood is used for model selection, and the posterior distribution is used for assessing our parameters after observing the data. Okay, so Bayesian regression. So what we'll do, let's see, I don't think I have enough, okay, time to go through in detail this, but I'm going to try and go through it a little bit quickly. But we're going to go through the multivariate case slower next time. The multivariate case, again, is the important one, but this univariate will show the basic steps that we're again going to transfer to the multivariate. And again, I think they're almost easier in a multivariate. Notice we're only doing one parameter here, we're not doing m. And this, you wouldn't do this, you wouldn't model like this normally. So let's assume that the intercept is drawn from a Gaussian density with a parameter alpha, giving the variance, yeah? So that's our prior density. P of c is just a Gaussian. No mean, so we just get c squared. The likelihood, and here I've put all the parameters in. So instead of w, we've got c and m, and then I've also got sigma squared in, is just the likelihood we had before. Seen this several times. Because we've assumed IID, we've pulled the sum up here as we've done, yeah, in our previous derivations. What do we need to do with these two guys to do Bayesian inference? Multiply them. Perfect. The posterior for C is given by the likelihood. Let me put my hands over those parameters for the moment. So you see P of t given C times P of C divided by P of t. Yeah? That gives you P of C given t. So the posterior for C, given the likelihood times the prior divided by the marginal likelihood. So the first thing we have to do, as was mentioned, is multiply them. The second thing we apparently have to do is this integral. But there's a trick, a really good trick, which means you don't have to do that integral. Well, you do, but you do it through knowledge of probability distributions rather than through actually sitting down and doing it. I mean, integrals are the hardest thing in some sense in maths. Not the hardest thing, but the hardest thing I've ever come across. They're not easy to do. And that's what limits Bayesian inference. It's the biggest problem for Bayesian inference. The framework's great, but as you start to get, we're being Gaussian about our likelihood and our prior, but we have to integrate at some point. If we're non-Gaussian, Gaussian's trivial. If we're non-Gaussian, the integral becomes difficult. But for the examples we'll look at, it's typically easy, and I'm going to show you the trick as to why it's easy. So this was what was said, multiply. And what I've done is replace that numerator with a constant of proportionality. Why can I do that? This means is proportional to. Why can I do that?
It's not dependent on your variance.
Perfect. The numerator is not dependent on C. There is a constant of proportionality there, but how can I find that constant proportionality? What must this distribution be with respect to C? Distribution being the key word. It's a distribution, so it must be normalized. Yeah, perfect. So if we integrate this distribution with respect to C, it must integrate to 1. That's true of all probability distributions. So when you write this constant, you're just acknowledging that. You're saying, it doesn't matter. What I'm interested in when I'm looking at probability of C, given the data, is the form of this density in C. It doesn't matter what the constant proportionality is, because once I've observed the form of the density, I know it must normalize. Of course, it does matter what the constant proportionality is because you want it for the marginal likelihood, but let's forget that for the moment. Just for the moment, bear in mind this trick. It's an important trick that you just look at multiplying the prior by the likelihood. How does that look? Well, in the top level there, and I'm running out of time, so I'm not going to do this in detail. Because C, this is the key point, so there's some nasty maths in there. It's not actually that nasty, but it may look nasty for the first time. How does C appear here? So, okay, an exponential multiplied by an exponential, right? What does that do to the argument of the exponentials? So if I have e to the a times e to the b, how can I write that as one exponential? E to the a plus b, perfect. So if we multiply these two exponentials together, we're going to get, ignoring the constant proportionalities again, we only care about c because c is on the left-hand side here. So ignoring these constants of proportionalities, we're going to get an exponential with something inside the exponential. Exponential times exponential is exponential, and that thing is going to be a plus b. So it's going to be one quadratic in C plus another quadratic in C. Yeah? Make sense? The sum of two quadratics is what type of polynomial? Not a trick question. Quadratic. So the answer itself is going to be quadratic in C. The answer of doing this, because of these functional forms, is going to be, this isn't obviously always true, this is the specific case of Gaussian prior, Gaussian likelihood, is going to be proportional to e to the quadratic in C. What density do we know that is of the form of e to the quadratic in C? And the answer's on the board as a clue. Gaussian. The posterior for C will be Gaussian. Now the trick is, why don't you have to do the marginalization, is because you know the Gaussian form. What you have to do next is sort that Gaussian into a quadratic that you can identify with a mean and a variance. Once you've identified that in that form, which is what this effort is here, so I've put log because I've got to just show what the term of the exponential is. And of course, because it's proportional to, that leads to a plus constant instead of a multiplied by constant. Yeah? So this is the key part. What I need to do is complete the square of this thing. So that's the multiplying out of C, which we're not going through in detail at the moment. We'll do it in the multivariate case. I need to complete it to be in this form. Because if I put e to this, what's the mean of this Gaussian? If exponential of that, what would be the mean of this Gaussian? Come on, come on. Yeah. Let me write it. Ah, that's the wrong flip chart marker. Oh dear. You're going to have to answer this question before you're allowed to go. I think this is a... what's the mean of this Gaussian? That's a Gaussian density I've written on the board, yeah?
Mu.
Mu. What's the variance of this Gaussian? The technical name for that is squiggle. No. I can't remember what that is. I think that's a variant on the sigma, which is probably not a good symbol to use for here. But it doesn't matter. We can define it to be whatever we like. The log of that is this, yeah? The constant term is just coming from the normalization constant. But the whole point is we don't care about the normalization constant, because once we've observed that the log of the density has this form, we know the mean and the variance. And you can go through that and you find that for this to be true, you have to complete the square on this. Yeah, that's completing the square. That's an A-level maths job, completing the square. Once you've completed the square on this, so you've got a quadratic form here, you're rewriting the quadratic form in this form. All quadratics can be rewritten in this form. And once you've got it in this form, you can immediately identify the mean and the variance. And in this case, that's the mean and that's the variance. The interesting bit is that this is very similar to the solution for C, as we'll see next time. We'll look at that briefly next time and compare it to the maximum likelihood solution for C. But suffice it to say that if you substitute in this guy here, and then you take alpha towards infinity, so that you get that improper prior we talked about at the beginning that I said you weren't allowed to do, you recover the maximum likelihood solution for C, which we've already looked at. So just to illustrate that quickly, I'll probably go through these slides at the beginning of next lecture. Your prior for C is this. Yeah? Now on the same axis, this is not normalized necessarily. It actually, coincidentally for Gaussians, is. But this isn't necessarily normalized in C, because C is on the right-hand side. So, but we can draw the likelihood. The likelihood isn't normalized in the parameters. So this is our prior belief for C, and this is the likelihood drawn in the space of C. What we need to do to get our posterior is multiply them together. If we multiply them together, which area are we going to get? The likelihood flattens, says that that's not possible. The prior says that all this stuff is less likely. Yeah? So the two of them combine together. The likelihood says, well, the data says this. The prior says, well, before I saw the data, I thought this. And the posterior, we know it's a Gaussian form, pops up in between. This is your updated belief of what C is, given one observation. Yeah? Which is what we were actually looking at the beginning of the lecture. We actually want to know the joint density over C and M. How are we going to do that? Which trick do we keep using? We're going to go to, come on, come on. Oh dear. Hard work this morning. Basis functions, just like we've done before. And we're going to use W transpose phi instead of looking at X. There's more references than that, I thought, in my slides. I've got the wrong set of slides up. Just to give you the... That's obviously not the latest version I'm showing there. There's the lecture very quickly. Sorry, yeah, I had the wrong set up. These are the ones that are online. That Thomas Bayes essay, you don't have to go and read that necessarily, but that's the original source for where that billiard table thing comes from, and he writes down Bayes' rule for the first time. Laplace also uses Bayes' rule for a coin problem. And a very similar coin problem is studied in Rogers and Girolami. So here's the reading, which is the other part. They do Bayesian inference for a coin toss example in Rogers and Girolami, and then they move into the linear regression example we're doing. To do that inference, you need to know about the beta density, which we haven't discussed, but you can still try and read through it because you use the beta as a prior and a posterior. And then there's some sections to read in Bishop as well. Okay, that's it.